We are the University of Maryland, Baltimore County, and our airplane is the Spudcraft. The fuselage was made using insulation foam and is covered with a fiberglass skin. It measures 52 inches from the tip of the nose to the end of the tail. The landing gear is a bar of aluminum that was bent to add clearance between the propellers and ground. The width of the main landing gear is 11.32 inches. It is screwed into the fuselage through two wood panels on both the inside and outside of the fuselage. The wing is also made from insulation foam and is covered with fiberglass and a strip of carbon fiber tow that acts as a spar for extra strength. Its wingspan is 60 inches and its chord is 12 inches. Both the horizontal and vertical stabilizers were constructed using foam board covered with a layer of fiberglass for added strength. The horizontal stabilizer spans 20 inches and the vertical stabilizer height is 9 inches. For Mission 1, the plane weighs 3.71 pounds, in Mission 2 the airplane is 5.61 pounds, and in Mission 3 the plane is 3.84 pounds. The center of gravity is approximately 3.5 inches from the leading edge of the wing. For the sensor lights, this decision matrix shows that the best choice was the bright LED with a lens. It was the brightest with the best viewing angle, giving it the best chance to be seen from the ground. To control the sensor lights, an ATtiny 45 microcontroller uses a channel from the RC receiver to conditionally drive three 3-watt LEDs. The sensor is powered by a 260 mAh 1S LiPo battery. The direction of the aircraft is controlled using ailerons on the wings and an elevator and rudder on the tail. The pushrod mechanism pictured is used to transfer torque from a servo to the control surface. The plane is controlled by an 8-channel FreeSky receiver. The receiver and servos are powered using a 1200 mAh 2S LiPo battery regulated through a 5-volt BEC. Commands are sent to the airplane using a Taranis QX7 transmitter. For the propulsion configuration, this decision matrix shows that a twin-engine tractor configuration was the best choice. The propulsion system is powered by a single 5800 mAh 4S LiPo battery which drives two 70-amp ESCs. The two Cobra 930 kV brushless motors each drive a 13x8 propeller. The motor and propeller combination was tested utilizing a watt analyzer and scale to measure thrust and power utilization. From this data, it was calculated that the optimal performance would be at 60% throttle in order to maximize speed while maintaining an endurance of 10 minutes.
For the sensitivity study, we predicted scores higher than ours, assuming other planes would be optimized for a single part of the score. The study showed that taking less time in the ground mission and Mission 2 increased the score exponentially, and all other variables only increased the score linearly. UMBC's scores were calculated based on the predicted scores of other teams. Our predicted scores are 1, 1.196, 2.017, and 0.5 points for Missions 1, 2, 3, and the ground mission respectively. The sensor has a missile-like shape with a pointed nose and 3 stabilizer fins at the rear. The sensor was built with 2 3D printed parts that connect in the middle with a twist and pull locking mechanism so that the electronics can be accessed easily. Decision matrices were used to decide on the number of fins and the type of locking mechanism. The winch consists of a spool, slip ring, and 360-degree servo mounted to a 3D printed base. The slip ring allows the spool to rotate without twisting the signal wires. A flat foam ramp covered with packaging tape to decrease the coefficient of friction was placed at the rear of the plane to guide the sensor during deployment and retraction. The sensor container went through multiple geometric variations in order to enhance stability, rigidity, and manufacturability while taking up as little volume as possible. A hexagonal prism was chosen over rectangular prism or cylinder based on this criteria. Airfoil selection started with researching pre-existing NACA airfoils. X-foil was used to compare characteristics between airfoils. The NACA 6412 was originally chosen since it had the most favorable lift-to-alpha characteristics at the expense of little added drag, but the NACA 2411 was ultimately chosen when material constraints forced a thinner airfoil. 3 aircraft configurations were considered: traditional, canard, and flying wing. Ultimately, the traditional configuration was chosen due to its superior stability, easy manufacturing, and abundance of resources to reference. The aircraft was 3D modeled, which allowed for precise CFD analysis of individual components and the entire aircraft. The takeoff and cruising parameters were discovered to be 29 miles an hour at 12 degrees alpha and 40 miles an hour at 3 degrees alpha, respectively.